All right, great. So we got another fun day for you today, full of activities. So a couple of quick announcements before we get started. The in-class HEC-RAS assignment, I believe, is due tonight at 11:59, the second HEC-RAS assignment. So if you have any last-minute questions about that, you can come contact me at office hours today, 5:30. So we're going to be covering the EPA Stormwater Management Model today. So this is going to be kind of another fun in-class tutorial slash, hands-on experiment. There won't be an in-class group activity today, but there will be a homework assignment you can turn in for extra credit, which will be due on the last day of class, Monday, December 6th. So we don't actually have class this day, but this is the official last day of class for the UT fall 2021 semester. So it'll be due on December 6th at 11:59 p.m. Okay, so I will just very quickly show you. So we're going to be working with EPA SWMM today. So much like the last two tutorials, I've posted the old EPA SWMM tutorial from a previous version of this class. I'm going to be diverging from this old tutorial pretty significantly, but you can follow along if you get lost. It still has some useful information here that'll help you through our tutorial today. So this is here under the activities folder on Canvas under files. For today's activity, you'll also need a hyetograph to put into the SWMM model. I've uploaded it under activities as SWMM hyetograph. Okay, so you can download this Excel file. We'll be copying and pasting this into the SWMM model today for our SWMM model run. I think I said that this was under, this is actually under documentation and files. Sorry, the old SWMM tutorial is under documentation. The hyetograph Excel spreadsheet is under the activities folder. And finally, I just want to show you where the extra credit assignment is in the Canvas files. It's under files, homework assignments, homework EC. Okay, and this describes the extra credit assignment. You have the due date December 6th, 2021. It's going to be using SWMM. You're basically going to be creating a SWMM model for this subcatchment that's part of the Austin flood flow area. You're going to be creating a SWMM model and simulating it and posting the output. So nothing especially complicated. This will be due on the last day of classes for the UT fall semester. And I will probably make this worth about a third of a homework assignment. So it'll be worth your while to do it, although it's not required, okay? Great. Are there any questions? It depends how comfortable you are with computers, with the EPA SWMM software in general. I would say like maybe 2 to 4 hours, 2 to 5 hours, maybe. It's really hard for me to say because different students will have different levels of comfort with the software. But I think it's definitely worth your while, especially if you've missed a homework assignment or have not done as well on homework assignments as you would have liked. That extra credit is there for you if you want it. Okay. Right. So are there any other questions? So the SWMM tutorial will probably not take all of the class period today. So after we finish with our run through of SWMM, I'm going to let you either work on this extra credit assignment or work on your group projects, given that you're all together. Okay. So without further ado, we can go ahead and get started unless there's any other questions for me just about today's lesson or anything at all. Okay, cool. So go ahead, let's go ahead and get started. I've already pre-downloaded SWMM. If you don't have it already, you can go under announcements, go under my latest announcement, follow this link, and then download the latest version of the EPA Stormwater Management Model, which is 5.1.015.exe. Go ahead and install that if you haven't done so already. So I'm going to go ahead and open up EPA SWM right here. So the EPA Stormwater Management Model is a really important model that's widely used in industry. It's the one that I'm the most familiar with out of the models that I've taught you in class today. The hydraulic solver that I wrote is comparable to the EPA Stormwater Management Model. And there's also another faculty member here at UT who's actually writing the new source code for the new EPA Stormwater Management Model. So it's still, there's various members of the faculty who work in this area. It's pretty important. It's widely used by cities for modeling flooding in urban areas. But perhaps more importantly, it's also used widely in cities for understanding water quality impacts of urban development. So the EPA Stormwater Management Model was first developed in around 1969, I believe. It's undergone several changes since then, but it was initially developed for the purposes of modeling combined sewer overflows. So I mentioned this a bit earlier on in the class, but combined sewer overflows are essentially when you have a combined sewer system in which the wastewater pipes and the stormwater pipes are combined. If those systems flood, it can release human waste and other contaminants into natural water bodies, which causes really serious problems for the aquatic ecosystems. And if you're a city and you get a combined sewer overflow, you can get fined for a lot of money. So it was initially developed for combined sewer overflows. There's a big emphasis on water quality in SWM. So if you're comparing SWM and HEC HMS, which I know there was a question on this earlier in the semester, what's the difference between SWM and HEC HMS? HEC HMS is more focused on like large hydrologic systems, so usually natural systems, maybe a very large river basin, for instance. SWM is very much focused on urban water infrastructure. It has a lot of functionality specifically for modeling networks of stormwater pipes. So HEC HMS puts a bit more emphasis on the hydrologic aspects of the system. It has more sophisticated models for infiltration, for instance, whereas SWM puts more emphasis on the hydraulics and the water quality side. Okay, so SWM, unlike HEC HMS, SWM really models like the complex hydraulics that you might see in an urban sewer system where you get backflow, where you get all kinds of time varying flow dynamics, and also pollutant transport through the network. So SWM is much more focused on urban water systems in particular. Okay, so that's kind of the difference between SWM and HEC HMS. There's also the fact that SWM was developed from another agency. So SWM is from the Environmental Protection Agency. HEC HMS is from the Army Corps of Engineers, and they have slightly different priorities. Okay, and those come through in the way that the software is designed. So are there any questions overall on SWM and its relation to other software packages? Yes. Right, so the EPA is more concerned with things like water quality degradation, degradation of aquatic habitats, pollutant transport, combined sewer overflows, whereas the Army Corps is more concerned with things like flooding, dam breaks, kind of those larger scale phenomena like that. Okay. But both are very widely used. Here in Texas, I see HEC HMS more emphasized. Where I came from in Michigan, EPA SWM was like basically the one that everyone used. Yeah. Because in the Midwest, there's a lot of problems with combined sewer overflows and water quality. Okay. Cool. Any other conceptual questions about SWM versus other models? Okay. Cool. So let's go ahead and get started. So I've opened up EPA SWM here. We're going to go ahead and we're going to create a model. So this is going to diverge a bit from the instructions. So within SWM, this model setup is very similar to HEC HMS. You have subcatchments, which represent land surface areas. And then you have two basic other component types. You have junctions and you have links. So links can represent things like conduits, pipes, channels, rivers, etc. The junctions can represent things like retention or detention basins, maintenance holes, manholes, any location where different links meet in the network. You'll also have structures like orifices and weirs, which are usually represented as links. And you'll also have junctions that can represent boundary conditions for the network. So that might be a downstream boundary condition like a free overflow, so a critical flow boundary condition, or a fixed boundary condition where you might meet the ocean or something. And so there's a fixed depth at that location. Okay, so let's go ahead and create a model. Oh, and I forgot to mention, aside from those physical components, there's also rain gauges, much like there are in HEC-HMS, which you populate with time series data, which we'll be doing, okay? So the first aspect we're going to concentrate on is the subcatchments. So these represent the land surface areas that we're going to model the rainfall runoff response on. You can create a subcatchment by going to this kind of shaded rectangle here. It says add a subcatchment. And we're going to go ahead and draw a subcatchment here. So the left click will create a vertex, and the right click will close your shape. So I'm going to go ahead and create a cool shape here. Let's make like a star or something. Okay, I'm just going to make a star. And the right click will close the shape. So we've got our subcatchment area there. Let's go ahead and modify the parameters of this subcatchment. And this is gonna diverge a bit from the instructions in the tutorial sheet. So let's change the name to S1 to indicate that it's a subcatchment. So I'm gonna just change the name. Oh, note, I got to the screen. You can either get to the screen by double clicking the object or by going in this list here over on the left. You can go to hydrology, subcatchments, and then select your subcatchment from that list. So yeah, the user interface is a bit easier to navigate than the HEC programs, in my opinion. So what we're going to do is we're going to go and change the area. I'm actually going to change the area to 500, and this is in acres. This area is in acres. There's some other parameters in here. We'll do rain gauge and outlet later. There's other parameters like the slope of the subcatchment, the impervious Manning's N, the pervious Manning's N. So you can represent inside subcatchments, you can have both an impervious fraction and a pervious fraction, and each has its own parameters. This width parameter here, this is kind of a fictitious width. So if you remember back to homework 2, I gave you a land surface and you were modeling the runoff wave from that land surface. So in that, I gave you a width of that land surface, which implied a length, right? And you could use that to route the runoff from the land surface to the downstream channel. In SWM, it's exactly the same. And as a matter of fact, what I had you program in homework 2 is the exact same way that SWM routes runoff off the subcatchment land surface. So that width defines the effective width of the subcatchment, which implies a length, and from that you can compute the runoff profile from the land surface. Yes.
Does that mean like regardless of like how big the subcatchment is, like if it's like all drains for like 100 yards of the river, like you could put 100 that would filter like all that water in that area?
Yeah. So and it also disregards the shape of the subcatchment. It basically assumes it's a rectangle with a given width and length, and then it routes it the exact same way that you programmed it in homework 2. Okay, so we set the area of the watershed to 500. Let's see if it saved that change. Okay, yeah, it saved that change. Okay, cool. So this is our subcatchment. It's going to represent the land surface area we're going to apply rain to. So the next thing we're going to do is we're going to diverge from the tutorial instructions a little bit. We're going to create a storage node. So you can think of this as being a detention basin, for instance. It's basically a reservoir. It represents a reservoir. So I'm going to go over here to this thing that looks like a reservoir. I'm going to click it, and then I'm going to place it right here. Okay. So we can go in again and let's modify the values. So I'm going to change the name to ST1, just to indicate that it's a storage node. Let's see, I'm going to set the invert elevation to 6 feet. So in hydraulic modeling, the invert elevation refers to the bottom elevation of your node. So it's the elevation of the bottom of the pond in this case. I'm going to change the invert elevation to 6 feet. I'm going to have a maximum depth of 10 feet. This is the maximum depth allowed in the pond. I'm going to leave all the others as 0. And then we're going to define the shape of the pond. Okay. So we'll go down here to where it says functional curve. If I click here, you'll notice it gives this equation for the area of the pond. Area equals A times depth to the B power plus C. So in this case, the coefficient is A, the exponent is B, and the constant is C. So let's have it have the same equation as in homework 5. So we'll let the coefficient be 1,000 and we'll let the constant be 10,000. So that means the bottom area of the pond is 10,000. And as the water level goes up, the surface area increases by 1,000 square feet per foot of depth in the pond. So it's kind of like a cutoff conical pond, basically. Okay. I'm going to go ahead and hit close after we've defined our, oh, sorry, actually one more thing. We want this exponent to be 1. By default, it's 0 for some reason. We want the exponent to be 1. Okay. Cool. So the next thing I'm going to do is I'm going to create a junction. So if you go here up to this menu again, you can add a junction node. I'm going to click on that. I'm going to click off to the right here. And much the same as before, I'm going to double click it. I'm going to change the name to J1 for junction. I'm going to set the invert elevation at 3 feet. I'm going to set the maximum depth at 10 feet. So a junction, it's similar to a storage element, except that it's meant to represent something like a maintenance hole or a manhole. It's kind of just a small element that you don't really model the change in storage inside the element. It's just kind of a small connector, basically. We're going to specify the invert elevation as 3 feet and the max depth as 10 feet. And finally, we're going to create an outfall. So this is kind of the boundary condition for the network. It's this little triangle here. I'm going to create an outfall node. Let's go ahead and put it over here. I'm going to double click again. We're going to leave the invert elevation as 0. And we can set the type of the outfall node here. I'm going to leave it as free, but there's several different boundary conditions you can use. So free assumes that it's basically a waterfall, so it goes over the critical depth at the outfall. Normal assumes that normal flow is reached at the outfall. Fixed is just a fixed depth. So for instance, if it terminates in a lake or something, it's just a fixed depth. And then you have tidal and time series. So this is if you have some sort of time varying boundary condition at the downstream end. So for instance, a tide coming in with the water rising in the ocean. Okay, so you can establish different boundary conditions. I'm just going to leave it as free. And let's change the name to O1 for outfall 1. Okay, so now what we got to do, we got to go back and connect these things. So I'm going to go back and click on subcatchment S1. And I'm going to change the outlet to the name of our storage element, which is ST1. And if I did that correctly, it will connect the two. So note that what I did here is I went into the subcatchment, I went to the outlet, and I changed the outlet to ST1, which is the name of our storage element. And it should create a connector from the subcatchment to the storage element. Next, we got to link up all of the other elements. So what we're going to do is we're going to create conduits to link them together. This is similar to what we did in HEC-HMS. Okay, so to create a conduit, we can go here, add a conduit link, and EPA SWM's interface works just like you'd expect. You can click on the storage node and then click on the downstream element to create a conduit. Oops. Wait a second. So click on the storage element and then click on the downstream junction. Yeah, there we go. And it should create a conduit between the two. So I'm going to go ahead and rename this conduit C1. We can, this is basically a channel or a pipe. We're going to let it be a pipe. We're going to let it be circular, and we're going to let the diameter or max depth be equal to 6 feet. So there's a big, basically like a big concrete pipe connecting these two things. Are there any problems, issues?
Where's the differentiation between shoulder and, or sorry, channel and pipe?
Sorry, could you repeat that?
How do we differentiate from channel and pipe?
Oh, there is no differentiation. It's just determined by the geometry you use. So there are closed geometries and there are open geometries. We're going to use this closed circular pipe geometry. And we're going to set the maximum height, which corresponds to the diameter. We're setting that to 6, and we'll leave everything else default. Next thing we're going to do, we're going to connect the junction to the outfall using the exact same method. And I'm going to go ahead and change that one. I'm going to change the name to C2. And I'm going to change the max depth to 6. Okay, so now our network's all connected. The last thing we need to do is we need to add a rain gauge. So to add a rain gauge, you can go and click on this little cloud icon here. And we can just place it over here. All right, so this is our rain gauge. We're going to set the rain format as volume. And our data source is going to be a time series. Okay. I think that's all we need to do here. I'll come back if there was anything else I needed to do. Okay, so now that we've created a rain gauge, we have to go back into the subcatchment and specify our rain gauge. So actually, if we go back to rain gauge, I'm just going to change the name to RG1 to specify that it's a rain gauge. And then I'm going to set the rain gauge for the subcatchment. If I go down here to this rain gauge cell, I'm going to set it to RG1. We're almost done here. Now we have to go into a time series editor. So what I did was I went over here to the left. I clicked on time series, and then we can click the plus to add a time series. So I'm going to call it time series 1. And we're going to enter data into this table. So SWM is kind of nice. We can just copy and paste from an Excel sheet. So remember, I uploaded that Excel sheet called SWM Hyetograph. It's over here in Files under Activities. You can download this hyetograph as an Excel file. And then the actual hyetograph is right here. So I'm just going to go ahead and copy these cells. So this is a 100-year storm. This corresponds to your solution for homework 2 for the ABM hyetograph. So I copied that. I'm going to go in here. I'm going to go ahead and paste it. So it should just paste right into the table inside of SWM. And this is at a 10-minute time interval. And I can view this hyetograph by clicking View right here. And it should look like that. And so this is the same alternating block method hyetograph you created in homework 2. Okay, with that, I can go ahead and hit OK. Now we need to go back into the rain gauge and set its time series. So I'm going to go back. I went back into the rain gauge by double clicking. I'm going to go and I'm going to change the series name to time series 1. And actually, I believe I need to change the time interval to 10 minutes here. I don't know if it's necessary or not, but I'm just going to do it. Okay, great. I'm going to go ahead and hit save at this point. I'm just going to call it CEE 365K in class tutorial. And let me know if there's any issues or questions, and I can pause and come around. Everyone's doing okay? So now we're going to go ahead and work, before we simulate the system, I actually want to go in and edit some of the simulation parameters to give you a sense of what SWM can do. So I'm going to go click on options here. I'm going to go down to general. So SWM gives you 2 different options, actually 3 different options for the hydraulic routing. It gives you steady flow, which is the static case. It gives you kinematic wave, and it gives you dynamic wave. So dynamic wave is actually just another name for the full St. Venant equations. So let's go ahead and use that. Let's go ahead and use the full St. Venant equations. It also gives you options for the infiltration model. We're just going to leave it as the Horton model, which is just a simple exponential decay. There's more sophisticated options you can use, namely green amps here for the infiltration. There's some other options here, such as allow ponding, which allows you to simulate flooding, essentially. Under the dates, we have to set the dates to correspond to our time series of rainfall, which is 01/01/2021. We're going to set the reporting start time to 01/01/2021. And we're going to end the analysis on 01/02/2021. Okay, and the other stuff we can leave as default. For the time step, I'm going to set the reporting step to 10 minutes. It doesn't really matter all that much. It's just the reporting step tells you the interval at which it will display the final results. Okay. We can leave all the others as default. The routing step is the internal time step used by the hydraulic solver. So if you're having issues with the model not being stable, you may need a smaller routing step. We're just going to leave it at 30 seconds. Okay, and here's the final thing we're going to look at. So under this dynamic wave tab, it gives you different simulation options for the St. Venant equations. For the inertial terms, let's set it to keep. So if you remember back to like the first day of class when we were looking at the St. Venant equations and its simplifications, remember that there were terms for the inertial forces, there were terms for the gravitational forces, the frictional forces, and the local losses. So basically, sometimes those inertial terms can cause issues with stability, so you may want to dampen or remove them from the simulation. We're going to say we want it to be as accurate as possible, so we're going to keep those inertial force terms. Okay. Great. The other stuff here doesn't really matter all that much. These are kind of details for the numerical simulation. Okay. And with that, I think we have everything we need here. So let's go ahead and try running it. I'm going to go ahead and hit this lightning bolt to run a simulation. And let's see what happens. Hopefully I didn't make a mistake somewhere. Oh, I did make a mistake. Recording interval greater than time series interval for rain gauge 1. Yeah. Oh, I did. Okay. Let me see. Reporting step, 10 minutes. 01/01/2021, 01/01/2021, 01/02/2021. Let me go back to the rain gauge actually, and I'm going to set this to the default, which I believe was just 1 minute. Let's see what happens if I do that. Nope. Recording interval than greater than time series interval for rain gauge 1. Okay, I got it to run. So what I did to get it to run was I went into general and I set the reporting step to 15 minutes. I'll go in and take a look at the reason for this error. But let's go ahead and let me just check the results real quick. I'm going to go ahead and plot a time series at the storage node at our storage unit ST1. To plot a time series, I can go over to this little graph icon of the red and blue lines and click create a time series plot. So note that I want node ST1 depth. I'm going to go ahead and plot it. Oh, that doesn't look right. Okay. Let me get a second to debug this. I'll let you know what happened. Oh, sorry. So for some reason it changed the maximum depth back to 10. Oh, sorry, it changed the maximum depth back to 0 in the storage unit. So I got to go and reset that to 10. I don't know why it reset that. Similarly, the max depth in the junction should also be 10. Let me try running it again. Okay, it looks better that time. Let's see. But yeah, okay, it worked this time. So for some reason, it reset the maximum depth in storage node 1 to 0, which caused no flow to go through the storage node. So
Did you change something else?
that was all I changed, yeah. I set my reporting step to 15 minutes. All right, so who's having issues with the simulation? Okay. So before I move on, I'm just going to show you quickly how to plot some of these things. So if you want to plot the time series at a given element, what you can do is you can click on the element, then click on the icon that's a red and blue kind of time series line, and it will give you the variable, the variable that you're interested in for that element. If you click edit, you can select which variable you want for that element. So I'm going to select runoff, and then I'm going to go ahead and hit OK to plot it. And so this is the runoff coming out of our subcatchment in cubic feet per second. Similarly, if I want to look at the depth in our storage node, I can go click on that red and blue line icon here. You know, if I wanted to edit the variable I'm looking at, I could do so, but I'm just going to look at the depth. And I can go ahead and plot it as follows. So note it rises up all the way to about 10 feet. So it fills up the storage tank, interestingly, and then goes back down. Okay, so I'm going to go around and help debug for anyone who's having issues with this. It can be a bit finicky. As I noted before, it for some reason changed the parameters in my simulation without me knowing. So I'm going to go ahead and come around and help.
For which part?
The time running, I'm saying.
This one's guys.
Oh, wait, now. Oh, wait.
Okay, there's one more thing I wanted to show you really quick before I turn it over to you, and that's how to plot, excuse me, can I just get everyone's attention really quick? So there's one more thing I wanted to show you, and that's how to plot a profile of the water surface. So you can actually animate the water surface within your network over time. So we can do that by going to report graph profile. We have to select the start node and the end node of our profile. So this is going to plot the profile along the length of the pipe network. How high is the water level going to be along that profile? Okay, so we're going to select our start node as ST1. We're going to select our end node as the outfall. We're going to go ahead and click find path. So it'll show us our path is links C1 and C2. I'm going to go ahead and say okay. And it'll show us this profile of the network from the storage node to the outfall. Now note that there's nothing here yet. Yep. The outfall, yep. So this is actually a bit hidden. It took me a while to find this when I was looking through this previously. Now we want to select the timestamp that we're interested in. To do that, what we actually have to do is we have to go over here and click on map. Don't ask me why. Okay, so we go ahead and select map, and then I can hit this play button to play the profile over time. And so you can see the water level rising during the storm and then going back down. Yeah, pretty impressive. So you can hit this play button, So to get to this, I went over here on the left, there's a project tab and there's a map tab. So I went to the map tab and then
How did you get the profile window?
yeah, so to get the profile, I'll come do it for you on your computer. So first, just go ahead and try doing the profile. And after that, you're free to work on either the extra credit homework assignment or your course projects, okay? Okay.
Or hydrologic spatial or
We
the,
tried both spatial.
so the spatial one's open in ArcGIS.
Oh, okay.
Yeah, and it might have its own .brj format.
Okay.
So it might have the same extension, I'm not sure. Yeah. Do you have a question?
Yeah. Screenshot.